Welcome to Differential Equations, section 4.1. In this chapter, we start looking at systems of differential equations. In question 1 here, we have a second order constant coefficient non-homogeneous differential equation, and they want me to transform this second order into a system. So you let x1 be x, easy enough. Differentiate both sides, and so x1 prime is x prime, and that's equal to x2. All right. So if I differentiate x2 prime, I get x double prime. And so now let's plug that stuff in. All right, so here's my original differential equation. I plug in what I know about x double prime, and that's x2 prime. And so you simply plug all that stuff in. Notice that for the plain old x, this is a x1. And so we're done. We have our system of differential equations where x1 prime is x2 and x2 prime is the relationship between x1, x2, and also 7t squared. All right, in this case, we're going to go and find the solutions to this particular system. We're also going to look at the direction field and some solution curves. So, x prime is 16y, y prime is 4x. So, we're first going to figure out what is the solution for x. So, x prime is 16y. So if I differentiate x again, that's 16y prime. And so now fill in what I know about y prime. And y prime is 4x. And so I get x double prime minus 64x equals 0. That's easy. Constant coefficient, second order. Form the characteristic polynomial. So r squared is 64, and the square root of that is 8. So I get two solutions, e to the 8t and e to the minus 8t. So that's the solution for x. So to get y prime, I simply plug in what I know about x. Okay, so it's 4 times this x. And so that's what you see here. And so if y prime is that, all I have to do to get y is to integrate it. So I've got a substitution here. I'm going to get out a 1/8 in the front. Here I'm going to get a minus 1/8 out in the front. But those reduce each to 1/2. And so we get our solution for that particular system. To get the solution field, I used this particular website. All right, and I'm going to enter in what I know about the system, and I'll show you that in just a moment. And when I did that, I got this as the flow field. So you can see the flows are fairly flat across here. In this region, notice they're coming in, turning, and going around. And so when I picked a few solution curves, I got this particular picture. And in this particular picture, you can actually see the curves and how they are moving, so that when you do MyLab Math and you want to pick out which solution curve is it, well, it certainly looks like solution curve A there. So use tools to help you out with this stuff. And so if I look at that tool, so this is what that tool looks like when you first go there. So right now it currently is just the differential equation, but if you click on this, you see you can then type in your particular system. And once you do that, so let's see, we can just make up one here, 7x. Okay, so I've got what that looks like, and now you could pick some initial starting points and just hit submit. How about 1, 1, 1, minus 3, 0. And so if we look at that, then you can see what the initial starting points and their trajectories would actually look like. All right, on question 3 here, we have a electrical network. I've got some resistances R1 and R2. I have an inductor which has 4 henries. I have a alternating source here, 100 sine 60t. And so they want me to figure out what the differential equation system would look like for this. Most of it's fairly easy. The only tricky part here is it says we have an alternating voltage drop, and the voltage drop, the key word there is drop, is in the direction of the current I1. So remember that when we have a network, it matters if I have a battery and I'm going that way, or if I am going this way. Make this a little bigger. So it matters if I am dropping down or going up. Here we have a drop down. That's why this is minus 100. I come across the inductor and they tell me the voltage drop down the inductor is L, which is 4, derivative of the current. But notice at the same time the current is coming this way. I've got I2 coming the other direction. And then I loop around and I've got the voltage drop across this 75 ohm resistor, and by Kirchhoff's laws, the sum of all the voltage is 0. And if I go across loop 2, all right, that's pretty easy. I'm coming across the inductor. All right, that's di2 dt. But at the same time, that's coming this way. I1 is going in the opposite direction. And I do have this voltage drop across the 100 ohm resistor. And so I do get my system of equations for this particular electrical network system. So this is our first look at systems in chapter 4.